All right, let's dive right in. We're going to talk about the absolute foundation of our modern world, Boolean algebra. It sounds complicated, but it's actually the super simple, kind of beautiful logic that's humming away inside every single smart device you use. So here's the big question, right? How can a bunch of simple on or off switches come together to create a machine that can do, well, anything? You'd think that's an impossible jump to make. But the secret sauce is a system of logic that's actually been around for over 150 years. To get how machines think, you first have to understand the world they live in. And it's a very simple world, a world that's pretty much black and white. Here's the core idea. In this digital universe, there are only two options. That's it. Something is either true or it's false. A light is either on or it's off. And to make it easy for machines, we just represent those two states with a 1 or a 0. There's no gray area, no kinda, no maybe. Now, the rule book for this world of ones and zeros is what we call Boolean algebra. It's named after its inventor, a guy named George Boole. And what's wild is that back in 1854, he wasn't thinking about computers at all. They didn't exist. He just wanted to create a pure algebra of logic to sort out complicated arguments. The most basic piece of this whole system is something called a proposition. It sounds fancy, but it's just any statement you can look at and say, yep, that's true, or nope, that's false. It has to be one or the other. It can't be both, and it can't be somewhere in between. Think about it like this. It is raining. That's a perfect proposition, right? You look outside and it's either true or it's false. Same for today is Monday. These simple yes or no statements are like the tiny little atoms that make up this whole logical universe. Okay, so we've got these little true-false atoms, but that's not very useful on its own. The real magic, the real power, happens when we start combining them. And we do that using just a few simple tools, which are basically the Lego bricks of all digital logic. We connect all our little propositions using just three main tools, or what we call operators. You can think of them like the plus, minus, and times in regular math. They are and, or, and not. That's it. That's the whole toolkit. To really see how these operators work, we use this awesome little chart called a truth table. It's basically a cheat sheet that shows you every single possible outcome. No guesswork, no ambiguity, just the facts. First up, we have the and operator. Now, this one's the tough one. It's strict. For any statement connected by and to be true, both sides of it have to be true. If even one little part is false, the whole thing comes crashing down and becomes false. And this truth table shows that perfectly. Remember, 0 means false and 1 means true. Just look at that output column on the right. See that? The only, and I mean only, way you get a 1, a true result, is on that bottom line, when both input x and input y are 1. Everything else gives you a 0. Okay, next up is the or operator. This one's way more relaxed. It's much easier to please. For an or statement to be true, you just need one of the parts to be true. It doesn't care which one. So if it's hot, you're good. If it's raining, you're good. If it's both, hey, that's fine too. And the truth table for or makes this super clear. Check out that output column. As long as there's at least one little 1 in the inputs, the output is a 1. The only way to get a false, a 0, is if both of the inputs are false. See the difference? And last but not least, we have the simplest one of all, the not operator. This one isn't about combining things. All it does is take one statement and flip it to its total opposite. It's an inverter. It's the opposite day operator. If something's true, not makes it false. If it's false, not makes it true. Its truth table is about as simple as it gets. Input is 0, output is 1. Input is 1, output is 0. That's it. It just flips the switch. Okay, so we have these building blocks. And, or, not. But, so what? What's the point of all this? Well, remember George Boole's original goal. It was all about taking messy, complicated arguments and making them simple. This is how we do it. We can take an everyday sentence like, I like tea, and just call it X. So, I don't like tea becomes not X. Once we turn our language into these simple symbols, we can start playing with them, just like in a regular algebra class. And this is the absolute key. Boolean algebra has its own set of rules that let you take a really long, clunky logical statement and boil it down to its simplest, most efficient version. It's like taking a fuzzy, noisy signal and filtering it down until it's perfectly clear. All right, now for the big payoff. How in the world did this 19th century logic puzzle become the engine that runs pretty much everything in the 21st century? For nearly 100 years, this whole thing was just a cool idea in a math book. Then, in 1939, this genius engineer named Claude Shannon had this incredible light bulb moment. He realized that the two states in Boolean logic, true and false, 1 and 0, were a perfect match for the two states of an electrical switch, on and off. And that changed everything. Suddenly, this wasn't just some abstract exercise on paper anymore. It had a real physical home in the world of electronics. So here's the journey, from an idea to an actual thing. You start with a real-world problem. You write it out as a Boolean expression. Then you use those rules we talked about to simplify it. And then, this is the magic part. That super simple expression becomes the literal blueprint for a physical electronic circuit, what we call a logic gate. So here it is, the big takeaway. Every single time you tap on your phone or type on your keyboard, what you're really doing is firing up billions of microscopic circuits that are just physical versions of and, or, and not. This simple logic from over 150 years ago is what makes our entire digital world tick. Which leaves us with a pretty mind-blowing final thought, doesn't it? We've managed to build this unbelievably complex technological world, all of it, on the simplest possible foundation you can imagine. A basic choice between yes and no, true and false, 1 and 0. It just makes you wonder, if we can do all this with just ones and zeros, are there any limits at all?